Okay, Daniel just came. Okay, 6:15. So as we said, we start. Okay, 6:15. Okay, so what I have in front of me is the summary file, right? Essentially, it's the same development as we did in last week's class. Okay, the difficulty with adaptive control often is it depends on which textbook you are looking at. So this is our README first file, right, which we discussed in lecture 1. And then if you go down, okay, so these are the reference books that are pointed to, quite typical, right? The book from Carl Ostrom and John Wittenmark, and that's the work from the team in Lund, Sweden. They had some very good work in adaptive control. Then second book is, of course, from my own group at Yale, Narendra and Anaswamy, right? And then also the pioneering the adaptive control development at that time was another group from University of Newcastle in Australia. So it really depends on which book you develop the materials. I mostly take them from the Ostrom book. Even the Narendra book, I don't strictly follow him, even though I'm from the same research group. Many things I do it my own way. All right, so in what we had done last week, right? So this is what we had done last week, looking at strict positive realness. Then last week was straightforward, and I didn't want to kind of make it too long-winded because it was mostly algebraic, right? Algebraic development. So remember what we had said. We said, okay, you look at the system, then carefully following algebraic development, but making sure you observe linear time invariant system type of operator rules, right? You saw that we came up to this essentially this diagram there, which I reminded all of you. I said, basically, this is very important because it is the basis for many things. And again, we would come up to this diagram, right? Okay, here you can say that in last week's development, I pretty much used the notation of my own Yale research group, right? Where the signal is coming from y, we label it as omega sub y and omega sub y dot, or ddt operate on omega y, then omega sub u and ddt operate on omega sub u, right? So though what would happen is that, okay, I would imagine you would also look at various different books, including the book from the Lund people, Carl Ostrom. Okay, so here in this file, which is the Note 03 summary, right? It's there. Right, so there was the completed Note 03, but also Note 03 summary, right? Okay, so if you now look at this summary file, which is basically a similar development, except using now the notation of the Carl Ostrom book, because many people refer to the Carl Ostrom book. So if you now look at it, the ideas are essentially in parallel development. So remember, we're looking for adaptive control of continuous time systems where only where we say only the input and output are measurable. So again, right, we pose the system to be controlled in this linear system form written with the DDT operator. So similarly, the RP polynomial or the pole polynomial is of nth order with the coefficients A1, A2 to AN, right? And remember, because we want to pursue a development with adaptive control, basically we are saying we do not know these numbers, A1, A2 to AN. All right, but we know the structure is nth order. Then the numerator polynomial we say is of m order, right? And then the B1, B2 to Bn coefficients we also say we do not know. In addition, what we do is we pose it in such a way that these polynomials are so-called monic. Remember what monic means? Monic just means that the leading coefficients are 1. All right. So if the leading coefficients are 1, that is always possible because I can pull up a coefficient Kp down here. Then that will make sure that indeed, you know, this numerator polynomial will be monic of degree m. Right. Then remember, we also define a number, an integer called the relative degree n star, which is the difference between the zero polynomial, the pole polynomial, and the zero polynomial. Right. And that's quite important because basically, when you begin to rigorously build together the proper stability theory, the relative degree 1 case permits you straightforwardly to use ideas from strict positive realness, and you can see how the design of the adaptive controller goes with the more direct stability analysis. It's not easy, but it's more direct. All right, and once you are clear about that, then you know you can begin to generalize to higher relative degree, which is not 1, and basically it's built on that. All right, and that's basically how adaptive control now is being done. It's essentially still built on the relative degree 1, except that you now build it in stages of backstacking. All right, and I will show you those as well. But never mind, we will rigorously handle it for the strict positive real with the case in which it will be very clear to you. Right, so that was how we posed the problem. System to be controlled, we don't know the coefficients. All right, RP of order n, ZP of order m, both monic, relative degree n star. Then remember the famous so-called, either you call it Diophantine or the Bijou identity. Then I said, look, you know, it's nothing more than polynomial division. So if you want, you can also call it the Professor PhD polynomial division identity, right? And that is basically saying that, look, you know, you already have the pole polynomial there, which is of degree n. And let's say you now begin to try to put out polynomial identity in this particular way. You first of all put together P polynomial monic of degree n. You put together an Rm polynomial monic of degree n star. Remember, n star is the relative degree, right? And then once you put this on the left-hand side, what this identity claims is that you will always be able to decompose this in the following manner as Rp times EP plus Fp, right? And then I said, look, you know, okay, we acknowledge that, you know, these were the famous people. Diophantine is probably a Greek mathematician. Bijou is probably a French mathematician. So when we acknowledge they were the first to see it. But I say it's quite easy to see. It really is quite easy to see because when you put it like that, on the left-hand side, then what you are having is, right, on the left-hand side, what you're having then is a polynomial of degree n plus n star. And if you view it in this particular way, that, all right, if you now on the left-hand side have a polynomial of degree n plus n star, and you divide it by a polynomial of degree n, so this is the divisor polynomial, then if you divide it by a polynomial of degree n, obviously you must get a quotient of degree n star, right? And then clearly, Rp will be monic of degree n, all right, which is what we have. Then the quotient clearly will be of degree n star, all right, and also monic. Then clearly you will have a remainder because you're dividing by a polynomial of degree n. So you will get a remainder, all right, of 1 degree less, but this polynomial will be of degree n minus 1, but not monic. Okay, so this is the so-called famous Diophantine-Bijou, but basically a polynomial division identity, which is what I mentioned. Okay, now we note that because this will be the design basis to bring us through. Whoops, why is somehow, okay, let me do. Okay, so this now is then an identity which will be used, but of course we have to be very careful, of course, to watch the rules of operators operating on linear systems. Specifically here, we are clear that at this stage we are not doing adaptive control. So all these rules pertain to linear time invariant systems. All right, so we then say, okay, fine. If that's the case, then I go back to my original system which you give to me, and I operate on both sides by the E polynomial. Right? Remember, E polynomial is monic of degree n star, and these are all constant coefficient polynomials. All right. Constant coefficient, basically linear constant coefficient polynomials. All right, so I certainly can operate on both sides with the polynomial operator of degree n star on both sides, and that doesn't change a thing because this is a linear time invariant system. So I would have no problems because linear time invariant systems obey the standard properties of linear superposition, associativity, commutativity. So, no problems at all. No problems at all. Right? Then I said once you have that, based on the Diophantine-Bijou polynomial division identity, I decompose that to be TRM minus F. This part I leave it as it is, right? Which is what we saw last week. Then I rearrange again. So this is TRM. All right. Then the basically the F y. All right. The F polynomial operated on y comes to this side plus QTZPU of t on that side. Right. Then I additionally note carefully. So remember from the above Diophantine identity, P is monic of degree n, Rm is monic of degree n star, F is the remainder polynomial. It is of degree n minus 1 and not necessarily monic. Okay, so Kp is just a number. E is of degree n star. N star is n minus m. Zp is monic of degree m. So therefore, clearly E times Zp is monic and of degree n, because n minus m and m will give me degree n, all right, of degree n. So this is therefore this I can just for convenience collect this together, label it as G bar, all right, the G bar polynomial, and this will be monic of degree n because this is n minus m, this is m, so it becomes degree n. Okay, so let's remember that. Okay, then I do one more thing. I look at this whole thing. All right, I look at this whole thing. I think Wang Xingying is having problems with Wi-Fi, keep dropping in and out. Never mind. Anyway, the session is being recorded. Okay, so we look at this. All right, and currently these are all proper because these are linear constant coefficient systems. All right, so far I've obeyed all proper rules. Then the next thing I want to do is I want to take this thing, right? Because when you look at this, this is basically a polynomial differential operator operating on a signal, polynomial differential operator operating on a signal, polynomial differential operator operating on a signal. Right. So basically, it's a set of signals on this side, well-behaved, a set of signals on the other side. All right. after you've operated on it, basically it's a set of signals. All right, and this is another set of signals, which is why, as I told you all, I said you all, many of you appeal and said you have signals and systems. I hope in your signals and systems you have carefully noted all of that, huh? Because basically we're using signals and systems ideas here, except I don't know whether in your the module that you took on signals and systems you observe this or not. Okay, so basically, you know, even though you say this is T, the T polynomial, Rm polynomial operate on the signal y of T, at the end of it, this is just a signal on the left-hand side. All right, and similarly, this one signal added to another on the right-hand side. So if it's one set of signals on the left-hand side, all right, an equivalent signal, all right, after we decompose it, another set of signals on the other side, there's nothing to stop me from saying that this signal on the left-hand side, I will filter by filter 1 over T, and I will do the same thing to filter 1 over T by the other side, except that for linear time invariant system, if I now want to filter on both sides by 1 over T, straight away one more condition comes in, all right? Whereas when it was just differential operator, polynomial operators operating like this, all right, I lose nothing because this is all correct. Basically, linear superposition is observed, commutativity is observed, associativity is observed, no rules are broken, all right? And when I come to here, all right, and I take this, well, basically an ensemble of signals on the left-hand side, another ensemble of signals on the right-hand side, and I say I filter both sides by filter 1 over T, and it's perfectly legitimate, except that when you now want to filter both sides by 1 over T, straight away one very specific constraint come out, because it's only meaningful to filter signals with a stable polynomial, all right, when you have them on both sides, because when you now construct the signals and you now filter by stable polynomials, all right, what then happens is that even if to begin with, when you set up the system on the left-hand side, on the right-hand side, if they start off with different initial conditions, as long as I'm filtering by a stable filter, the same set of signals on the left-hand side and right-hand side, nothing is lost, because even if there are difference in initial conditions, the filter is stable, initial conditions die away exponentially fast, so it doesn't matter at all, because these two set of signals, insofar as their non-homogeneous response are concerned, is identical. All right, but okay, this is only true if now when you filter both sides by 1 over T, Tp is constrained straight away to be a Hurwitz polynomial, stable polynomial. Right, but as I said last week, I said no problem, because later on Tp is a polynomial that in designing your adaptive controller, you will have to choose. You will choose that Tp polynomial, what you want to use in your design, completely up to you to choose. So no problem at all. You just remember to choose Tp to be a stable polynomial. All right, once you have that, then okay, you filter that, then basically it simplifies to this. Then this is another important expression, as I told you last week. After you filter both sides by 1 over T and simplify to this, then I rewrite it like that. I pull up, okay, I pull up the Kp out, all right, of the curly bracket. Okay, then to begin with, F was of order n-1 and non-monic anyway. So if I pull up Kp, F bar will still be of degree n-1 and still non-monic, except its leading coefficient has changed. Okay, G bar is monic and of degree n. So when I pull Kp out, this is of degree n and monic. Kp is of degree n also and monic. So I can decompose G bar over T, all right, because, you know, this is monic of degree n, this is monic of degree n. Therefore, when I decompose it, it's just 1 plus G1 P over T, where G1 now is not necessarily monic and of degree n-1. Okay, then I said, let me write out the whole thing properly. All right, so basically, if you expand it, it will look like that. I said, let me write this whole thing out properly. And then I said, when you write this whole thing out properly and stare at it, I said, okay, now we have now by a set of properly constructed differential operator operations, we have now rewritten the system like this, right? And then I said, look, in this curly bracket, how wonderful it would be if we can somehow exactly make everything in this curly bracket to be exactly equals to some k star times RT, where R is the reference signal that you send in to command your control system. All right. So I said, how wonderful it would be if we can make it like that. All right. And particularly, we would specify that, you know, your K star is the type of perfect gain, although unknown. All right. Is a type of perfect gain such that when you take K star multiplied by KP, it will be exactly equals to a number Km, which you will be using. All right. Km will be chosen by you. You will be using. But there's no problem because, you know, KP is from the original system. Km, you can choose any number you like. All right, this is just a KP is just a number. Km is a number you choose. And if KP is just any number, of course, there will exist some number K star such that KP times K star equals to Km. So no problem at all. All right, on this part. So now the question is, how do I make this exactly equals to K star times R, which was leading to the main thing that we did towards the end of last week's class. Because we said, look, you know, the moment you're able to do this, then you end up with your algebraic operations to make the closed loop exactly equals to this. And that'll be wonderful. Km you choose. Rm will be basically a reference model operator polynomial that you choose as well of degree n star. Km you choose, Rm you choose, and then finally, you know, with the way that you have arranged the differential operator operations, you made it such that if you are exactly able to do this, okay, then what would have happened is that you exactly get this as a result, which is wonderful. I mean, that says that, hey, I'm able now to directly control the output of my system via the command that I put in, and that's specified via Km and Rm, which is what I choose. Okay, so that's wonderful. Okay, now, of course, this critically depends. Okay, on the fact that this can be done, which is what we did towards the end of last week's class. We said, okay, rearrange that part. So what that says is that, all right, you have to construct, all right, so we basically are taking this and say it has to be this. So we rearrange this. And then we say, okay, it's possible if somehow I can construct a ut equals to minus ft over y minus g1p over tu plus k star times r. All right. Then I said, okay, let's make sure we really can see how this is being done. So remember, TP is monic of degree n, chosen by you to be a stable polynomial. All right. So similarly, this TP down here. Fp is not necessarily monic of degree n minus 1. G1 is not necessarily monic of degree n minus 1 as well. K star is just some number which has to meet this matching condition. All right, so let's see how we do it. So I said, okay, let's see how to make this control realizable. And to make it very, very clear, I said, why don't, instead of trying to confuse ourselves, let's just take the specific case where n is of order 2. N is of order 2, and let's begin to actually graphically see what happens. All right, okay, so now this is where I begin to, it's basically the same thing, except there I use the notation omega sub y dot, omega sub u dot. So here it's the same thing, except I use the Carl Ostrom's book notation to say when you take y and pass through 1 over t, we call it y superscript f1. Is this the same thing? It's the same thing, all right? Previously, last week, I called it omega sub y. So this is y superscript f1. Same thing. All right, just a notation difference. Okay, so let's call this signal like that, and let's see how we will build up a structure to do this. So we have the TP polynomial for which we are doing the filtering. Remember, we choose this to be stable. We choose All right, so we build it like that. We build it like that because we are going to have to generate the signal, right? We're going to have to generate the signal y superscript f1, which is basically the signal y passed through the 1 over t filter. So let's build that. Let's build this. Okay, so what we do is, as I told you last week, basically we build it using a state variable controller canonical form realization. All right, you all should know, because you know all of you are supposed to have 5104 or equivalent, and I just saw also in the Zoom list my two very hardworking undergraduate students are there. Evening there, I saw him there. I saw also my other undergraduate student Chua Wei Xian, also very hardworking there. They took 4302. Then I also saw the other students who took 4302 from me, Zhong Jialun, Pao Li Chen, then Huang Yibo, So Yibo. Okay, hopefully everything is fine. His parents are here, he told me. Okay, then Wang Xiaoxia is also there. Li Haifeng is there. Then so that on there I can see the other list. Okay. Tang Ziwei is there. Okay. So they all took 4302 from me last semester, which is equivalent. So they also know controller canonical form very clearly, and they can build this up, right? We can build this up quite straightforwardly. So let's build this in control canonical form. I mean, it's not difficult. I mean, you do this. Then basically, if you want to write out the state variable equations for the controller canonical form, what happens is that the signal coming into this filter is y of t. This is your t filter, basically. All right, and then what comes out is your y superscript f1 and y superscript f1 dot, right? This is basically your method 1 realization, we call it in 4302. Right, so you can build that. I mean, basically you can build that. And similarly, you build the same thing for u. All right, one more control canonical form, 1 over t filter, right? And then except that the signal coming here is u. Okay, so now you see for the second order system, the signals that you need for fp over t p would be f1p plus f2 1 over tpy. All right, this we already denoted to be omega sub y or y superscript f1, and this is simply pre-operated on y superscript f1. And then you go back and look at your control canonical form filter. All right, these are exactly the state variables that you generate in this control canonical form. All right, so you generate this, you have these signals. So you needed to have f1, all right, multiplied by this signal f2. They are there from your control canonical form realization. Similarly, the u signals are there from your control canonical form realization signals. All right, so whatever you need down there, all right, this is now the second order n equals to 2 specific case of your perfect control law. All right, your perfect control law, if we go back to what we had, right, this is from last week. We said we wanted this. Okay, so for the second order, when you put it in second order, all right, that perfect thing that you wanted is exactly now written out in this way. Then that was when we went on to draw the diagram. We said, let's look at that in the diagram. All right, so the diagram is, I guess, this is a system you're trying to control. You can only measure the output signal and the input signal. The output signal you put into the 1 over t filter realized in controller canonical form. Out of it comes y superscript f1 and y superscript f1 dot or ddt operate on y superscript f1. So this will be the state variables, all right, coming out of your control canonical form filter. All right, this is your control canonical form filter taking this signal as its input. Similarly, an identical control canonical form filter taking u as its input, u superscript f1 coming out, ddt of u superscript f1 coming out, and these are the state variables coming from your second order control canonical form filter. So these signals you can generate, all right, from your y and your u building the 1 over T filter. So these signals you have. Then we say, okay, go and stare. Go and stare very, very carefully at the signals that you require. Right, the signals that you require are these. All right, F1 times this, basically Y F1 superscript F1 dot and Y superscript F1. So F1 times this, F2 times that. This G1 times this is U superscript F1 dot and G2 times U superscript F1. Right, and then we say, okay, if it's this, let's look at the diagram. All right, so it's exactly F2 times this and F1 times this, G2 times this and G1 times this. Then of course we still need the additional part, which is the K star times R. All right, so you saw that because these are all the signals that are needed. All right, in your perfect control law, so to say. All right, perfect control law. You still need a K star R. So we draw that into the diagram. K star times R. So we take all these things, feed it back here, these two things, feed it back here, these things, feed it back here. And with this, then this would have exactly implemented your perfect control law that you want to exactly now get for you. All right, that perfect closed loop behavior that you wanted, because when you can put in those perfect numbers, all right, when you can put in those perfect numbers, we saw, all right, what then would happen is that once you get that, all right, we will exactly get this perfect closed loop looking like that, which is, you know, what we would want. Okay, this is what we would want. Okay, assuming that indeed, all right, assuming that indeed, okay, in that diagram, now, all right, you are able to put perfectly these numbers, K star, G1, G2, F1, F2. And if you know the system, the coefficients in your pole polynomial, A1, A2 to AN, if you know the coefficients in your zero polynomial, B1, B2 to Bn, you can calculate this. Except that we're saying, no, in adaptive control, we don't know the coefficients of the system. So even though we know this exists, we cannot calculate it because we don't know the values of the system coefficient. But never mind, even though we don't know, we know that these numbers exist. All right, and this is very nice because basically system given to me, you tell me I can measure U, you tell me I can measure Y. I can generate this is just the 1 over T filter in control canonical form. I can generate this is the 1 over T filter in control canonical form as well, with U as input, Y as input. I get these signals out. So getting all these signals is no problem. Only problem is what are the gains. And this is where we can start doing adaptive control. Because now, okay, we know that these gains exist, except we don't know what they are. Then we can put in time varying numbers. All right, and we can now begin to look at a procedure now to put in the time varying numbers and then how to adaptively update the time varying numbers. All right, the same kind of diagram. All right, same kind of diagram. Okay, then remember, so this was what we finished up to last week, and I didn't want to push on further because, as I said, I wanted you to just stare at this diagram. I just wanted you to stare at this diagram because, you know, it's a basis for proceeding, even though it's basically second order, but it generalizes, it completely generalizes. So remember, I then asked you to carefully look at this. Okay, then I uploaded again this summary file. In this summary file, of course, we push on further, right? So clearly the perfect control law can be done. All right, if you extend it to nth order, it basically, and reorganize it, it basically looks like this, right? So, and because we don't know those perfect numbers, we put in time varying gains, all right, and adapt them. But insofar as the control law is concerned, you know what the control law should be because the control law will basically follow the arrangement of this diagram. All right, which is written out. Basically, it is just it's just exactly like this, right? F2 times the first signal, F1 times the second signal, G2 times first signal, G1 times second signal, K star times R. So if I now rewrite this, okay, it will be just F1 times the YF1 dot, F2 times YF2 dot, G1 times UF1 dot, G2 times UF1, and then K times R, except I made this time varying now. So just arranging it this way. All right, all that I'm doing is exactly as in the diagram, except I've rearranged it in this linear and the parameter form. All right, these are all the signals we know, because this will be exactly the signals you would generate. All right, for second order, you will generate 2 signals here, 2 signals here, and 1 signal here. In general, for an nth order system, you'll be generating n signals because your T will be n. You'll be the control canonical form 1 over T filter of nth order. So you generate n signals here, you generate n signals here, and then 1 more signal here. Okay, so basically, you know, n signals here, and 1 signal, 2n plus 1 signal. N time varying gains here, n time varying gains here, and 1 more time varying gain. So n plus 1, 2n plus 1 time varying gain. So this is basically your control law. You're putting in the time varying gains, but of course we have to decide how to adaptively update it. Okay, so this is now moving one step further from what we said at the end of last week. How do we generate the adaptive law? Okay, so when I re-uploaded the summary file for you, I said please stare carefully at the diagram. Please stare very carefully at the diagram. All right, that's why I didn't want to push further. Okay, and you stare carefully at the diagram and look at it very, very carefully and properly. All right, there are 2 very important properties that are there in this diagram. 2 very important properties that are there in this diagram. Okay, the first important property, all right, which I just said, label this as an intermediate result, a proposition. I said, look, you know, remember we said, okay, if T is of order n, you put this in control canonical form, there are n signals that come out. T of order n, control canonical form, n signals come out. So n signals down here generated with Y coming in, n signals down here generated with U coming in. So 2n signals. And these 2n signals are not, you know, any signal. Basically what you will generate is basically YF1 dot, all right, and what will come out? This is control canonical form, right? Method 1 realization. Okay, so what basically comes out is that there will be n signals up to DDT or to the power of n minus 1 operate on YF1. All right, then UF1 and DDT to the power of n minus 1 operate on UF1. So n signals down here, n signals down here, and these are the n signals that, okay, n signals down here, n signals down here. So these are the n signals and n signals that you will be using in your control law. The first thing that comes out, all right, which is a very important property, okay, very, very important property. That's why I asked you to stare carefully at the thing and think through it deeply. It turns out that when you generate the signals in this way, n signals, these 2n signals have a very, very special property when you generate them in this way. It turns out that these 2n signals now, the way they are generated, actually are an equivalent set of state variables for the system that you are trying to control. All right, these 2n signals are the state variables of the system that you're trying to control. Remember, what is the system you're trying to control? The system that you're trying to control is an nth order system like this. All right, and then you generate those 2n signals. And now one very important property which I'm telling you here is that these 2n signals are not just generated. These 2n signals together actually form a state vector of your system that you're trying to control. And I ask you to think carefully again. Okay, I ask you to think carefully again. Remember, the system that we're trying to control is nth order. Then I now tell you that these two n signals that I generate form the state vector of the system. So clearly, these are the state variable signals, but your system is nth order. So clearly, this is a non-minimal realization. Okay, this is a non-minimal realization. That's the first thing. All right, that's the first thing. It's a non-minimal realization. Okay, more than that, I want to push on further. Very, very important. That's why I just wanted to stop at this diagram down there. So in general, for an nth order system, n signals down here, n signals down here. So this is n equals to 2. So that's why it comes out like that. So basically what happens is that these things together form a state vector of this system, all right, that you started off with. But it's a 2nth order non-minimal realization. That's the first thing. That was in proposition 1. Okay, that was in proposition 1. Okay, then look at what's happening. I'm taking this signal multiplying by a gain. 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 So I'm taking these 2n signals multiplied by gains and then feeding that back. What is this? So go back to your 5104, no, sorry, 5101 linear system. Okay, my students here, go back to your 4302, again, linear system. All right, you take state variables, multiply by gains, and then use them to construct your input. What is this? This is state feedback. Except this state feedback is under the non-minimal realization, but never mind, it's still state feedback, it's still state feedback, it's still state feedback, okay? And one important property that you should remember, all right, whether 5101 or 4302, state feedback does not change the order of the system. You're going to check carefully all the developments you did, whether in 5101 or what we did in 4302. All right. State feedback does not change the order of the system. Okay. This then brings us to the second important result, proposition 2. Okay. Because I'm now doing state feedback, but the state vector is of order 2n. So state feedback will not change the order of the system, which means that the closed loop now will be of the same order as my state vector. It will be of order 2n. All right, of order 2n. So I do state feedback. Of course, you know state feedback gives you a set of poles after state feedback, closed loop poles after state feedback. And I'm doing it under a 2n order non-minimal realization state feedback. So when I close the loop with state feedback with 2n state variables, order remains the same. So the closed loop now must be of 2n order. Where are these 2n poles? Okay. These 2n poles, all right, you will be able to show, all right, you will be able to show that these 2n poles are exactly all there. They are at the poles of TP, which is what you choose to begin with, and you have to choose it to be stable. You have to choose RM, relative degree n star. You choose it to be stable. But in the way that we are doing it, one immediate constraint comes up. It is also at ZP, which is the zero polynomial of the system. So at least in this way that I'm attempting to construct an adaptive controller, all right, I am constrained by the fact that I need to work with systems with stable zeros, the so-called minimum phase system. But never mind. All right, let's begin to build and do this down there. Let's check that it's really of order 2n. TP is of order n, so the n is there. RM is of order n star is n minus m. This is of order m, so n minus m plus m is n. So all my 2n poles are there and accounted for. All right, okay. So this is basically very, very important thing that is there. That's why I wanted you to stare carefully and think about this particular diagram, because the way it's constructed retains some very, very important properties. Basically, these two important properties. All right, these two important properties. And with that, all right, okay, first of all, proposition 1 and 2. All right, proposition and 1 and 2 and the building of this thing is not restricted to any relative degree system. All right, it works for any n order system, it works for any relative degree system. All right, but now using proposition 1 and 2, and as I told you to start with, using strict positive realness to show you, first of all, how more straightforwardly, it's not easy, but more straightforwardly, I can build up an adaptive control for using strict positive realness. So for the specific case of relative degree 1, all right, I can show that, okay, basic reference model will be this. This reference model is not restricted to relative degree 1, but if it is relative degree 1, then the system is strictly positive real. Okay, so basically, in general, your reference model will be like this. But if you're working with a relative degree 1 case, then you also have the additional property of strict positive realness. All right, then what you can then do is you can state adaptive controller can be constructed in this very direct way. All right, you can still construct an adaptive controller for higher relative degree, except it doesn't come out in such a direct way. You have to build it in stages, which is basically the research area nowadays on building backstepping methodology into adaptation. All right, and next week I'll show you basic developments of backstepping. But today, no. Today I just want to concentrate on getting this done. And once we get this done, we indeed will be able to show again that we have uniform stability in the entire state space. And in addition, we get the guaranteed tracking error. Okay, we get the guaranteed tracking error. So this is the only thing that afterwards I will carefully push forward, but I will also show you how to carefully take the steps to prove these two intermediate results. Okay, that's all I want to do in this first part. Let me now very quickly okay, so thank you, Daniel. So with that, let me go back and say again what I said. I said, okay, so we carefully develop these things again. All right, basically, well, last week we had built to the stage where we carefully put together this diagram. All right, and then this week I just earlier taken it a stage further to say, you look carefully at this diagram. All right, the signal Y, all right, for an n order system, you're taking the signal Y, putting it in, all right, pass through a 1/T filter in general of order n. So n signals come out. You take the signal U, again put through the 1/T filter, all right, in control canonical form, all right, of order n signals will come out. And then I said, look, this was carefully and deliberately done in this way, carefully and deliberately done in this way, all right, n signals and n signals, 2n signals. And I said, okay, these 2n signals, all right, actually form the state vector of your system to begin with, except it's 2n order, so it's a non-minimal realization. All right, then the next thing I said, okay, go and stare at the diagram again, which is why I just wanted to leave it at that and ask you to think carefully, think deeply. All right, then I say look carefully. All right, these n signals, 2n together form the state variables of a 2n order non-minimal realization. And all that you're doing here is you take each signal multiplied by a gain. All right, and then you take this and use this to construct the control input signal. So what are you then doing? These 2n signals are the state variables. All you're doing is multiplying them by gains. So you're doing state feedback. Okay, and you go back and check your 5101. My own students, go back and check your 4302. State feedback does not change the order of the system. So now you are doing state feedback in a 2n order non-minimal realization. Your closed loop is also of 2n order. And after you do the state feedback, basically you have a closed loop. All right, so where are the 2n order closed loop poles if you put in these perfect gains? They are all there, All right, this will be, they are all, and they are at the roots of the T polynomial of order n. Remember, T you choose, and you choose it to be stable. All right, then Rm you choose, you also choose it to be stable. Okay, here is where a constraint is met. All right, the other set of poles are also there at Zp, which is the zero polynomial. So in the way that we are doing this constrains our approach to be applicable to systems with stable zeros, or the so-called minimum phase systems. All right, but no worry, no worry. Basically here, the main thing is to illustrate that, okay, this is how we will do adaptive control with input-output system. All right, input-output system. Okay, let's count and make sure that indeed there are 2n. TP is of order n, and up to you to choose. All right, so stable. Rm is of order n star, which is n minus m, and for you to choose. Okay, Zp is of order m. N star is n minus m, and m gives you n. So you see all the 2n poles are there, and these are where they are located. So you can clearly see also this will influence your design. All right, this will also influence your design, and in a way, all right. Remember, I told you, I said, okay, first of all, lecture 1, we developed the idea simply in first order system. Then lecture 2, we generalized the thing to a state feedback system with full state variables measurable, right? Then I said, okay, very natural to now extend this now, see how to extend this to a system where state variables are not measurable, but only input and output are measurable. And we've done that. All right, except we have to do this in a special way. Whereas in 5101 and 4302, if you wanted to do the same thing, what would happen is that you would construct an observer. Here you cannot construct that same observer because you don't know the system. To construct an observer, you need to know the system. Here you don't know the system. So you cannot construct that kind of observer. But then you just finished seeing what I've just said. I said, on the other hand, I still am able to construct an equivalent set of state variables, except it's 2n order. So effectively down there then, all right, embedded in there is a different kind of observer. In fact, typically, if you look at the adaptive control textbooks, all right, they would refer to the T filter as a state variable filter, because out of it, they are generating equivalent state variables. So effectively then embedded in there is an observable structure, but of a different kind. All right, of a different kind, not completely equivalent. All right, so you see state variables are generated. All right, and then if you want to see again where the relationship is back to how you would see the observer. All right, remember in your 5101 and in your 4302, if we had pushed on further, when you construct an observer, finally in the closed loop with the observer, what will happen is that in your closed loop, based on the Kalman separation principle, all right, Kalman separation principle, first of all, would be your alpha O of S, which will be your observer poles. Then alpha C of S, which will be your state feedback poles. This is the same down here. Okay, basically the T sub P is there. These are the equivalent of your observer poles. That's why the TP is basically called the state variable filter, the observer filter. All right, and then the remaining poles are there, constrained by this structure, and this is basically the equivalent to your alpha C of S. All right, so as I said, you know, okay, if you just had 5101 or you had 4302, you are stuck because you don't know how to do an observer. But as I told you, I said adaptive control, we got to work harder, work harder. So you see, we have now in a different kind of way been able to do that. And with that, now we are able to push ahead. Okay, so as you saw, all right, what we then did is, okay, remember, as I said, this diagram here, constructing this thing, all right, is general. It's not restricted to any relative degree, all right, not restricted to relative degree equals to 1, not restricted, all right, for any general and any relative degree, this is correct. All right, Then we prove the properties. All right, you will see that in proving, I will go on to showing the proof of the properties. In proving these properties, this is also not restricted to relative degree 1. So this is true for any nth order and any relative degree. Proposition 1 is true. Proposition 2 is also true. All right, then you move on. And the closed loop reference model can be built to be like this. This again is not restricted to relative degree 1. All right, not restricted, because for a general relative degree, for a general n order system, the closed loop will also become like that with the perfect control gains. Except that, especially for the case of relative degree 1, it will now allow me tonight, all right, to proceed to rather straightforwardly show you, all right, how the adaptive controller is built. All right, at least now you can see the thing. As I said, you know, that's not the end of the thing, because now that the way ahead you can see it. Then for general relative degree, you basically build an app to it in a backstepping manner. All right, one more strictly positive real stage after another, and that one I will show you next week. I'll show you next week. Okay, for today, we now say, okay, now let's look at the particular case of relative degree equals to 1. And that's also what you'll be doing for your CA1. All right, for both 5104 and also 6104. All right, in recent years, I've decided no point, because all that happens with the backstepping is that you add a lot of additional signal processing. It doesn't tell you anything new. All right, it just shows you a lot more signal processing. So in the early days, I used to force the 6104 people to do a lot more signal processing, but it's no use, it's no use. In more recent years, 5104, 6104, you're still doing relative degree 1, seeing the ideas, but still for 6104, I want you to dig deeper and tell me what's happening inside. Okay, so relative degree 1, if it's relative degree 1 and the closed loop comes out like that, if it's relative degree 1, you can know that, okay, this is strictly positive real, and then you can put an rather straightforwardly a first stage adaptive law like that, and indeed, all right, indeed, we can get that uniform stability in the entire state space, all right, in the entire state space, and we can guarantee also the tracking error convergence that we want. All right, so with that, let me bring you to, as I also promised you, the parallel development is there. So this is same thing in the typewritten notes, all right? So building this up, operator notation, 1 over t needs to be stable. So it's all there, it's all there, it's all there. All right, just to show you. Okay, so relative degree 1, all right, relatively straightforward. Haris, this is the Malay dialect of Singapore. So my students, Wishen, who is Singaporean, will attest that for you. So now I'm using English, using Mandarin, but also using the other language in Singapore, Malay. All right, so Daniel would probably also know a bit of this. Daniel, our undergraduate previously from mechanical engineering, now of course graduate student in our class. Okay, so I will actually look on carefully to develop the stability and convergence for relative degree 1, and build on that actually is the next stages, which I'll talk about next week. But for this week, I'll just concentrate on this. Okay, very important now. All right, very important now is what I told you was the 2 intermediate results. That, all right, the signals that I generate, n signals here, n signals here, I said these are not ordinary signals. These now together, when you collect them together, this is a state vector of your system, albeit 2n dimensional non-linear, non-minimal realization. So this is proposition 1. Okay, I wouldn't go into detail to prove. It's not difficult. Basically, what you have to carefully do is take the thing, rewrite in operator notation. All right, if you want to show that the signals down there, those 2n signals now form the state variable realization, you have to carefully collect them together, organize them together, and there will be this gigantic matrix. All right, and if you now collect together this gigantic matrix and write it out, all right, which is what I tell my students in 4302, and I'm sure in 5101, if you have listened carefully, it should be there. You take these 2n signals, and you make sure that somehow you're able to organize them such that these 2n signals appear here, and all the related numbers from your zero polynomial, from your pole polynomial, and also from your T filter, because your T filter is your observer filter. All right, they will all appear down here, arranged in some particular way. All right, and then you show that basically you're able to arrange this so that this signal, now all these 2n signals appear on the right-hand side with numbers, with the external input. And then on the left-hand side, they appear again in first derivative only. With that, then you have proved proposition 1 for me. All right, not difficult, not difficult. All right, if you go and look in the uploaded materials, as I told you, my previously I had a very hardworking GA, Mr. Sun Lu. Now, of course, Dr. Sun Lu. He has carefully also proved this proposition for you, specifically for the case of the relative of order 2 in your CA1 more comprehensive write-up. So you can also see it down there. All right, so not difficult to prove. All right, so go and do some work after tonight to put this together. Meantime, also look at Dr. Sun Lu's file. All right, let's go and see. Dr. Sun Lu, the assignment. All right, so as I said, go and look at the additional CA1 briefing notes. All right, this one by Dr. Sun Lu, and inside down there, you will see that he essentially has properly now put the proof of proposition 1, but specific for the second order case. All right, but basically the ideas are the same. Okay, so not difficult, but some work for you to do. Okay, then with that, then once you have that, then it's not difficult. Then you go about and really construct this diagram. So that's why I want you to carefully keep this diagram in your mind. Go construct this diagram, construct the state feedback, and then when you construct the state feedback, carefully now track all the equations involved, and you will be able to now also prove proposition 2. All right, proposition 2 showing that indeed with state feedback, order of the system has not changed. Therefore, all the closed loop poles will be of order 2n under the perfect situation, and this will be where they are. All right, so you will also be able to do that, and I also leave that to you. Similarly, all right, similarly, Dr. Sun Lu, previously my GA, has also proved it for you in this second order case in there. All right, so you can go and look at that in there, because with that now, I'm able now to push on, because with that, once I have that, then I'm able now to carefully look at what I have developed, which is second order case. All right, let's say second order case. All right, shown in this way, but in general, in nth order case, okay, second order developed in this way, in general, in nth order case. But now I will specifically look at the situation for relative degree equals to 1, because as I said, all right, as I said, okay, I just want to very clearly show the key steps in there. And if relative degree 1 is easier to see, all right, easier to see. And then, as I said, you know, for higher relative degree, the only difficulty is that you have to do a lot more signal processing. Each stage is a backstepping stage, all right? And then basically you are concatenating strictly positive real stages, stages after stages, and then building it along to get your equivalent result. All right, so I want to show this carefully, which is the thing that now I will do next. All right, so remember, as we said, all right, with proposition 1 and 2, all right, okay, so this is the reference model you are using. Okay, and we are saying it's of relative degree 1 now. We're looking at this specific case. This is the reference model you are using, which will look like that. You can check this is strictly positive real. All right, adaptive law now for this case actually very direct, which allows us to see the key ideas. And now with this adaptive law, with generating the controller like this, but putting in time varying gains in there, and then adapting it in this particular manner, I will now proceed to show you that again, we achieve uniform stability over the entire state space, and we continue to get guaranteed tracking error equals to 0. Okay, and you will be able to experiment with this exactly in your CA1, both for 5104 and 6104. But again, I say that, look, this is the key results I've obtained. All right, so I guarantee you tracking equals error equals to tracking 0 equals to 0. But this is not the whole story, okay? Because when you do your CA1, you will see, okay, it behaves exactly what we want, okay? Existence of solutions is guaranteed, all right? Stability in the entire state space is guaranteed. You are getting the guaranteed adaptive tracking that you want. But there are many more things in the system down there. Many more things. Of course, they are well behaved, but there are other issues there to be investigated, and I particularly therefore expect 6104, 5104. I just want you to learn from there, observe these things, and report your observations, analyze your observations. 6104 people, all right. Next week I will mention a few more things, and I expect you to look in there to tell me, hey, what other additional things need to be observed. Okay, never mind. With that, first we push on now to look at stability analysis. All right, for relative degree equals to 1. Okay, and again, first of all, Daniel, I want to thank you again, because has happened before in my other classes where I forget to hit the record button, and then the students say, oh, you're prof, the other part missing. But as I said, also no worry lah. Because I operate in a very kiasu, what we say in Singapore, right? What we say in Singapore, our own local language is not Mandarin. It is our own Singapore dialect in a kiasu way. So I'm and a fail safe. Kiasu basically means fail safe. All right, where you can see that I make sure that my properly recorded sessions, they are all down there. So thankfully, still thankful to Daniel that I didn't miss it. But if I had missed it, you can go to these links and see that. And you may still want to go to these links and see, because the lecture 3 class last week in class, I didn't want to kind of be too long-winded, but you see in Zoom, I'm able to do that more carefully. So this one in Zoom, if you go to lecture 3 class, in the previous Zoom, you will see that by hand, I did step by step all the algebraic steps, even though they are simple, but there by hand I did it. Okay, so anyway, here now, let's come to stability analysis. All right, for this relative degree 1 case to show that, all right, because I had claimed, right? I had claimed that, okay, if we now set up the controller in this way with time varying gains, all right, I said that. Then I said, okay, if you now set up your reference model in this way, because it's relative degree 1, all right, and you set your adaptive law in this particular way, I said we are guaranteed uniform stability, existence of solutions in the entire state space, and we are guaranteed convergence of the tracking error. Okay, let's prove that. Let's prove that. Okay, and this one, as I said, tonight is going to be rather longer class, because this one you have to track it very carefully. Okay, so let's see what we're doing. Okay, first thing to do is to note that okay, this is what we are trying to control, written in operator notation. Then remember we have proposition 1. Okay, with proposition 1, it then tells us that, all right, the 2n signals that we generate, that this form the state variables of the system. All right, so okay, let's write out those entire 2n signals. All right, let's write out those 2n signals, and let me go back to my Yale University notation. We call that omega. All right, so remember there are 2n signals down there. All right, the basically they will be the omega sub y all the way differentiated up to n-1 times, so n signals. Omega sub u differentiate n-1 times up to n-1 times omega sub u. All right, so two n signals here taken together, forming the omega 2n order omega vector, which is your 2n order non-minimal realization state vector. All right, so from proposition 1, I know this system can be written like that. And just to remind myself that, look, you know, this is the non-minimal realization, okay? So now let me write down, as I said, you know, the, remember it can be proved, right? As I told you before, it can be proved because if you now go to, right, as I told you, you go back to the notes down there. It's not difficult to prove proposition 1 and 2. All right, not difficult to prove proposition 1 and 2 because all that you need to do is now carefully take the whole thing, write out the whole thing properly, and it will be some gigantic matrix looking like this. And this is exactly what I'm writing out, although I don't write out the detail. But basically, if I write it out, all right, it will be like this, okay? So now that will be that same gigantic matrix, and I write it as AP, all right? And I remind myself it's a non-minimal realization by putting a triple bar on top, all right? Okay, then of course, plus, all right? Then of course also the B matrix, of course now being a single input system, this is B sub P. And I remind myself it's also a non-minimal realization, all right? And similarly, the C matrix, all right, transpose, okay, times the 2n order non-minimal realization omega. Okay, so I just remind myself that, look, you know, I already know from proposition 1 that my system with the signals that I'm generating is written in this 2n order non-minimal realization. All right, then my control law was taking the time varying gains, multiplying by these 2n signals, taking the scaling gain, but also as a time varying gain, multiplied by my set point signal. All right, so no problem with that. Then as usual, we already know that a perfect set of gains exists. So no problem for me again to rewrite the time varying gains as first of all, one part which is the perfect gain, all right, plus another part which is the error in the time varying gain. So we've done that before, all right. And then similarly, this k star, the perfect gain, plus p sub k of t, which is the time varying part. All right, so I just take this and write this out. All right. Okay, then of course, let me remember. So even here, let me remember that these are non-minimal realizations that I'm working with. All right. Okay, then we know that once we put these things in, all right, once we put these things in and we separate out, oops, all right, and we put these things in and we separate out the perfect part, all right, then basically, all right, we know that when we put in the perfect numbers, all right, that this will exactly get us the closed loop that we want. All right, so I separate out, and when I separate out this perfect part in this particular way, right, when I separate out this perfect part in this particular way, okay, I want to remind myself that these are non-minimal realizations. All right. Okay, now when we separate this out, okay, we already know, all right, that when you put the perfect gains, you get exactly the reference model that you want. All right, so what that means is that, all right, now here, now that I've written it in this particular way, with this perfect gain, this now will be exactly the A matrix of the reference model, but also in non-minimal realization. That's why I want to remind myself that this is a non-minimal realization. Okay, I want to remind myself. Okay, clearly now this will be the B matrix of the non-minimal realization of my reference model. And here, this will be straightforward. This will be basically the C matrix of my non-minimal realization. Okay, and I have to remember that, okay, because you will see what then comes up later. Okay, then we already know in proposition 1 and 2, all right, that once that because these are the non-minimal realization, that the exact gains will result in that state feedback giving me the perfect reference model closed loop with the perfect gain, and the perfect gain will now give me the reference model, except that now this reference model is itself now in a 2n order non-minimal realization. So I want to be careful down here. So basically with the perfect gain, it will give me exactly the reference model. All right, because we saw that that with the perfect gains, all right, with the perfect gains, it gave me the reference model. All right, let's remind ourselves. Right, so this is where we said, okay, if somehow you're able to make it a perfect set of gains, all right, if you're able to make it a perfect set of gains, and you also saw it down there, all right, with the perfect set of gains, okay, this is of course specialized to order equals to 2, but the whole idea was that if you now, all right, use this perfect set of gains, you were getting this exact closed loop. All right, and you can see this is exactly how you're setting up the reference model, Rm. This Kp star is equals to Km. All right, so that's why, you know, when you put in this perfect set of gains, this is exactly what you're getting. And this is what I'm stating and using now to say, okay, you know that when you put the perfect set of gains, when you put a perfect set of gains, all right, the perfect set of gains here, perfect set of gains down here, you get the reference model. Okay, you get the reference model. ECR just came. Okay, you get the reference model. All right, so you get the reference model. Okay, so this is exactly the reference model. And since it's exactly the reference model, and actually the reference model now basically has all the 2n poles, all right, has all the 2n poles, all right, and those 2n poles in the closed loop, as we said, these are the 2n poles, all right, of the complete reference model, all right, except that, all right, what then happens is that because it collapses to a minimal realization of relative degree 1, they are there, except you don't quite see them, but they are there, okay? So then the reference model itself all basically is under 2n order state feedback. So it is of 2n order resulting in this closed loop. It's a 2n order system, which means that if this reference model, even though it turns out to be relative degree 1 and in that simple manner, but basically embedded in that is its own 2n order non-minimal realization. So that's why I emphasize that, and I have to keep track of that. All right, so it has its own 2n order non-minimal realization, right? So I better remember that. Okay, so what then happens is that the reference model, all right, will have its own, all right, 2n order vector of state variables. Okay, so these are its own state variables, and then it will be possible to write it, all right, as a non-minimal realization with its 2n poles, am triple bar, all right, plus bm triple bar and cm triple bar transpose. All right, I just want to emphasize that these are under a non-minimal realization. So remember, all right, remember, as I say again, you do the arrangement in this way, you put in the perfect gains. You do the arrangement in this way, you put in the perfect gains. This is for the system, a 2n order non-minimal realization. You put in the perfect gains, all right? you are doing state feedback in a 2n order non-minimal realization. Except that you also know, based on propositions 1 and 2, that all right, in this 2n order state feedback realization, when you now put in the perfect gains, you exactly get the reference model. And you also know from proposition 2 that, okay, the reference model, because it's 2n order, it must have 2n poles, closed loop poles, and the 2n poles are exactly as stated for you, all right? Exactly as stated for you by that proposition 2, right? By the proposition 2. Okay, which means that even though you can write your reference model for in transfer function form, in in strictly positive real form, or in a simple manner, but internally in this arrangement, it itself admits a 2n order non-minimal realization in this way. All right, is there. All right, so by propositions 1 and 2, this 2n order vector for your reference model exists. It exists. All right, your reference model. Okay, there's a big difference here though. All right, compared to lecture 2. In lecture 2, when you generate your reference model, you can use its state variables. Here, the only thing you know is that as a theoretical result, this exists. All right, but there's no way you can exactly build AM triple bar, BM triple bar, and CM triple bar, because now this is a different analysis and a different way of realization altogether. All right, the only thing is that, all right, theoretically, all right, by proposition 1 and 2, the result exists, and this non-minimal realization, 2n order non-minimal realization of this reference model exists. And particularly now, if we are looking at a case of a reference model, a special case of a reference model with relative degree 1, we can make this strictly positive real. And then now we can push on to do the relatively straightforward development of the adaptive controller. Okay, let's see how we do it. All right, so now remember, right, we have the system, all right, with all the time varying gains feedback, all there, we've stated out down there, carefully written it down here. All right, we have also noted that, okay, even though the reference model in transfer function form, you may be able to write it in a simple way, but internally it carries with it a 2n order non-minimal realization. And if you want to know what the numbers, if you know all those numbers, you can actually compute this out and build it together. But you don't know the numbers, so you cannot, it's not like lecture 2 where you can build this, but theoretically this exists and we will use this. All right, so we'll use this. Okay, so let's see. Okay, here clearly to analyze the system, all right, we will be interested in looking at the actual 2n order signals that we generate. These are the actual 2n order signals that we generate. Okay, it's the first one. All right, and we're using this. These are actual ones. Then this is the conceptual one of the reference model, which we know exists, but we cannot lay a hand on it because we only know of its conceptual existence and we can write it in this way, but you cannot use it in the design. So it's not like lecture 2. In lecture 2, you can use this in the design. Here you cannot. Here you cannot. You only know that you can keep track of this theoretically, all right, but you cannot use it in your design. Okay, you can use the output tracking error in your design because certainly you can measure the output of the system. And of course, you generate your reference model, right? You generate your reference model in this particular way. You also have your reference model output. So the output tracking error you have. This one you don't have because it's only conceptual. Okay, so then, okay, let's see what we do. Let's see what we do, and I will carefully keep track of the various parts of the non-minimal realization. Okay, so let's keep track of that. So from above, all right, if I now okay, in terms of development, there are some parallel developments in lecture 2, all right, because what I will certainly do is, this is certainly correct. This is certainly correct. This now becomes AM triple bar, BM triple bar, and CM triple bar, and then plus all these error terms in there. So this part is correct, 3.1. Okay, then this part, of course, is also correct, except it's conceptual. Okay, it's conceptual. Okay, but even though it's conceptual, there's nothing to stop me from using the same methodology as in lecture 2 to take 3.1 minus 3.2. If I take 3.1 minus 3.2, all right, I'm now able to get an expression for the error in the state vector. All right, so let me carry that carefully. All right, you can, okay, after tonight, you carefully go and check, take 3.1 minus 3.2, and you should be able to see that it comes out in this particular way. Okay, so I remind myself that, look, these are non-minimal realizations. All right, okay. And you take that and you'll be able to see that, okay, what then comes out there, all right, is this parameter error, P of T, all right, transpose, then parameter error just in the scaling gain. Okay, then now, all right, to make my notation more compact, to make my, so that the terms are not all over the place. All right, so now remember, these are the errors in the 2n gains in the state feedback. This is the error in the scaling gain. All right, so there are 2n errors here for the state feedback gains, all right, which is P transpose. Then, sorry, 2n errors in the state feedback gains, all right, P, and one error in the scaling gain. So let me collect this whole thing together and call it P bar. All right, so this is P bar is of order 2n plus 1. All right, then these are your 2n signals. All right, your 2n signals. N here, these are your 2n signals. Okay, these are your 2n signals. Oops, sorry. All right, so 2n signals here, and then of course the R signal associated with the scaling gain. So let me also collect this together as a 2n plus 1 vector and call it omega bar so that my writing is cleaner. So now if I write this cleaner, now it will turn out to be like that. Let me again remind myself that I'm working with this non-minimal realizations, right? Okay, and the important thing is, as we already saw, here, 3.1, is that, look, this one together gives me AM triple bar. Okay, these two together gives me BM triple bar. This thing is the same as CM triple bar. So this triple of state matrices, AM triple bar, BM triple bar, CM triple bar, although of dimension 2n, nevertheless, this triple AM, BM, CM, they are the state matrices of my reference model, even though my reference model may simply be written in transfer function form in this manner. All right, so this AM triple bar, BM triple bar, CM triple bar are the state matrices of a 2n dimensional non-minimal realization of my reference model. Okay, so with that, since now it comes out to that, and I have the same AM triple bar, BM triple bar, and CM triple bar, all right, I go back and say, look, you know, so remind myself that I'm working with that. So CM triple bar, AM triple bar, 2n dimensional, BM triple bar. All right, so from above, we have already seen that, look, these are the matrices of your reference model. And what was your reference model? Okay, in this particular case, just very simply, Km in transfer function form over Rm of S. All right, so even though in transfer function form, it comes out very simply, embedded in there is this entire 2n dimensional non-minimal realization equivalent. And all right, if now we are looking at relative degree 1, all right, we know that for the relative degree 1, this particular reference model, all right, is strictly positive real, which is the result that I will use to develop the first direct adaptive control analysis. All right, so remember this is now strictly positive real, which is what I'm going to use next. Okay, so my adaptive law, remember I've chosen it to be, all right, we've shown that, you saw that, all right, we said that the adaptive law now for relative degree equals to 1 now. So now this relative degree equals to 1 now. All right, that the adaptive law now will just be like this. All right, so if I say it's like this, let me show that indeed this will work. So this is my adaptive law. All right, theta bar dot. All right, the whole thing, 2n plus 1 signals. The 2n signals multiply down here the time varying gains and one more signal multiplying this. All right, so 2n plus 1 signal, all right, equals to minus signal kp. Gamma is 2n by 1, 2n plus 1 by 2n plus 1 strictly positive real matrix. Omega bar was the 2n plus 1 set of signals which I've just mentioned to you just now. All right, these signals down here. All right, the 2n signals from here, 2n signals from here, and plus 1 signal from here. All right, so omega bar is that. All right, and then just multiply by the output tracking error. Okay, how does that work? Okay, so because it's relative degree 1, I can show it more straightforwardly. So in that sense, in a way, even though it's conceptual, I can put together a Lyapunov function candidate, because Lyapunov function candidate, I don't have to measure those things. I just have to basically conceptually put it together and show that it's possible. All right, so now let me look at this Lyapunov function candidate, which is now E transpose PE. Okay, and this E is the state error vector between the 2n dimension state signals that you generate, n signals here. So this is the state error between the 2n signals that you generate and the 2n signals which are theoretically there, guaranteed to be there in your reference model, but you don't have a handle on this. You don't have a handle on this, but theoretically they're guaranteed to be there. So I can still define the state error. So I'm using it. All right, I'm still using it, even though, you know, I cannot measure it, but never mind. I said, okay, I'm still interested in E transpose PE. All right, and I'm still interested in the parameter error, right? 2n plus 1 parameter error, P bar transpose, right? P bar transpose gamma inverse, because remember I said that I will use a gamma 2n plus 1 by 2n plus 1 symmetric positive definite matrix down here, right? So I use a gamma inverse down here times P bar. Okay, and in addition, because now my reference model is strictly positive real, all right, my reference model is strictly positive real. In addition, I have from the Kalman-Yakubovich lemma, all right, which we had seen earlier, that okay, for this reference model that I have, all right, that this is indeed equals to the diet minus Q transpose minus epsilon L, which I can simply, you know, because I don't need this decomposition, I can simply put it as equivalently minus Q. All right, except it's very different. I don't specify Q down here. I just know it exists. All right, I just know it exists. Okay, so that happens. Then I go ahead, all right, and similarly go ahead and go and develop it in a way, all right, similar to lecture 2, except I must note in detail that in terms of the signals I have, I must be very clear. So now, okay, similarly as before, all right, now E dot, all right, from above turns out to be AM, all right, E plus 1 over K star. This is from 3.1 above, all right, B M, all right, triple bar, V bar transpose omega bar, all right. You can check from 3.1 above, it turns out to be like that. And as before, so I won't do it again as before, all right, this P times AM triple bar. I won't do it. I did it in lecture 2. I can decompose it in this particular way, a symmetric part and an anti-symmetric part. All right, then that turns out to be like this. All right, plus the remaining part. All right, plus the remaining part, which is down there. Okay, you can track that carefully, and that will turn out to be 2E transpose 1 over K star P BM. Okay, let me remind myself. All right, that look, that's the non-minimal realization of the reference model. So I still have that. So it turns out to be like this. All right, so up to now, borrowing a similar development, all right, borrowing a similar development from lecture 2, but here, next step, this is where it becomes different, because now what I need to do now is look back in there, very, very carefully look back in there, all right, remembering from earlier that in the way that I specify the K star, remember earlier I specified the K star was, you choose Km, there exists a Kp, all right, you choose Km, there exists a Kp, so of course, some K star exists such a K star Kp equals to Km, right? And this is the K star down here. All right. So what you then need to do now is to note very carefully that, all right, now we are looking at the particular case. All right, we are looking at the particular case of relative degree 1. And in relative degree 1, all right, with strict positive realness, this is the first result from Kalman-Yakubovich lemma that we will use. But remember, Kalman-Yakubovich lemma has a second result, that, all right, in your state realization, and your state realization was basically AM, for the reference model, AM triple bar, all right, BM triple bar, all right, and of course, the CM triple bar, all right, and that Kalman-Yakubovich lemma says, okay, if this is strictly positive real, all right, if this is strictly positive real, okay, if this is strictly positive real, then this is the first result I have, all right, and if this is strictly positive real, okay, if this is strictly positive real, if I now just change it a bit, if I change this thing a bit and multiply by my BM triple bar by 1 over magnitude of K star, all right? So K star is any number, magnitude of K star is positive. 1 over magnitude of K star, which is positive, is still a positive number. So now if I take the reference model, which is AM triple bar, BM triple bar, and CM triple bar, which I know to be strictly positive real, if I multiply this by just a positive constant, strictly positive realness still remains. All right. So, okay, what that says is this is the first result which I will take from my Kalman-Yakubovich lemma for this ABC matrices, which is strictly positive real. But there's a second result which says that, okay, this P that comes from it, take this P, multiply by your B vector. And when you multiply by your B vector, because the D vector is equal to 0, or the gamma is equal to 0, so basically you take this multiplied by the B vector is exactly equals to Cm. Okay, let me remember all the all right, exactly equals to that. Okay, so now this is where this will come to help me. All right, basically now a simple method to note that typically with your reference model, all right, it is not too difficult to say like no loss of generality, certainly no loss of generality at all to say, look, let me pick a reference model, reference relative degree equals to 1, a stable pole polynomial, and I pick this to be a positive number, right? Because look, you put your set point in this direction, you want your output to move in the same direction. So no loss of generality, okay? So, okay, Km is positive. No loss of generality. All right, so here, if Km is positive, all right, not difficult for you to quickly check, all right, in terms of pure numbers that, all right, if Km is positive, all right, sine of Kp and sine of K star will be exactly the same. That's the only way in which that relationship can hold. All right, so I have that. Then now I go back to what I actually have if I simplify it down there. in my expression down there. All right, so now you can see that Kalman-Yakubovich lemma tells me that this particular second part of the Kalman-Yakubovich lemma tells me that this part is exactly equals to Cm triple bar for that specific triple of matrices down here. All right, exactly. Okay, so with that, then I note that then okay, it's straightforward for you actually now to carefully now work out all the terms and all the signs here and all the terms and all the signs here. And now because we appeal to the property of strict positive realness, right? Because we are able to appeal to the property of strict positive realness. Similarly now, by design, this is our adaptive law. By design, our adaptive law in this whole set of terms allows us to cancel this term, all right, leaving us now with what we require with the sign definite term, which is like this. All right, then the rest of it basically is not difficult, all right, it's not difficult. Okay, there's a E1 down here, all right, make sure that I get all the terms correct. All right, then you can see indeed, certainly this cancels each other out. All right, leaving us with the sign definiteness, and indeed now getting you what I promise. Is the result. All right, that with strict positive realness, right? With strict positive realness, we get these things. All right, we get these things, and we get that uniform stability in the entire state space, right? In the entire state space, and we get the tracking error equals to 0. So you've seen that down there. Okay, let me say just a little bit more. All right, just a little bit more, then I will finish off. Okay, let me just say a little bit more. So now, basically, indeed, as we saw, right, which is also here in this note, right? Carefully doing that, basically the same thing, except I've done it very carefully. All right, so now we get this result. So for the relative degree 1 case, this is now the entire result is summarized here. All right, it is basically guaranteed existence of solution and stability in the entire state space. All right, and we get the tracking error equals to 0. And basically this page, all right, if you just want to do your CA1 straight away, all right, and start exploring what it looks like, this page is enough for you to go ahead to do it. All right, this is the summary for relative degree 1 case. Okay, as I said, let me just finish off by saying that, okay, we've done it for relative degree 1. All right, and it was straightforward because we could use the ideas of strict positive realness to show, all right, how that was achieved. Okay, it doesn't stop there. If it's relative degree 2, the whole thing still proceeds, all right, except that you have to do a lot more signal processing, and basically is added in another stage, which is basically a backstepping stage. So if you now look at the whole thing very carefully, all right, we have now completely proved the whole thing for relative degree 1. But if it is not relative degree 1, okay, we cannot use strict positive realness. You go back and check. Propositions 1 and 2 are still correct. They're independent of relative degree. The fact that your reference model will still turn up to be Km over Rm of S is still correct, except that when Rm of S is no longer of relative degree 1, all right, and you have now got to make it of relative degree higher than 1, this is no longer strictly positive real. So the straightforward stability analysis that we've just completed does not hold. Okay, so you have to do a lot more, all right? And here, as I said in the earlier years, I used to punish the 6104 people. Okay, everything is correct. So here, when it's relative degree greater than 1, the controller does not change. The controller is still the same because we know that you put in perfect gains, whether it's relative degree 1 or not relative degree 1, it doesn't make a difference. It is still correct. Proposition 1 and 2 are still correct. So the control law does not change, but adaptation has to be done differently. All right, because the very direct adaptation that we were able to do, all right, which was just very direct like this, all right, because we build on strict positive realness, you are not able to do that. You're not able to do that. So now you have to do a lot of equivalent backstepping type of signal analysis to get back for you stage by stage equivalent strict positive realness. So you see the adaptive law now requires a lot more signal processing, and this was previously no, ignore this now, because even for 6104 I let you do relative degree 1, except I want you to dig deeper and understand what is happening. All right, so it will be like that, and stability analysis is done stage by stage. There's a first stage like this. All right, then there's a second stage whereby you really have to look at signals and systems. All right, basically, basically ordering. Okay, it's like a ordering relationship of tracking signals, but also subject to linear systems. All right, and basically now you are carefully looking into signals and system in a very careful way. Okay, I'll talk more about this next week. For now, most important is that we have reached this stage where we have definitely got for ourselves an adaptive controller with only input-output measurable. All right, and basically this is the structure for the second order, and this is exactly your CA1, and you build your CA1 like this. And actually, you can start experimenting with it already. But don't worry, as I said, don't be in a hurry. In recess week, my GAs will be there, all right, to basically give you detailed briefing on both CA3 and CA1. All right, then next week's lecture class, I will ask my GA to also attend, because next week's lecture class, I will use it to start briefing you on your CA3 and also your CA1. I start briefing you. All right, I'll start briefing you next week. Next week is lecture 5. Why is that? Because Prof Ho needs to start early. So next week is lecture 5. I will still take it, but lecture 6, Prof Ho will start to come in. All right, Prof Ho will start to come in because he needs to come in earlier because of some of his own timetable scheduling. So week 6, lecture 6, he will come in. Then recess week, what will happen is that my GAs will give you the detailed CA briefing. Then after recess week, the so-called week 7, I will come back one more time, all right, where I will show you some of the further ideas ahead, all right, because we're not able to. Last time, I used to be very tough. I used to cover everything, make everybody suffer. But now I'm kinder. Now my plan is to show you very clearly the key steps, because after you learn the key steps, it's not difficult for you to carefully read the rest of my materials and then know how to build on from there. All right, it's not difficult. So after recess week, where my GAs will give you the briefing, the next week, week 7, I will come back and I will discuss matters further ahead. And I will also, on that week 7 lecture class, I will also now lay down and tell you very specifically for the exam for my part, Okay, so the week after recess week, when I take the lecture, I will tell you exactly for my part, which parts are for exam and which parts are just for reading only. Okay, so my 4302 students know how I do it, because that's how I did it for them last semester as well. So that would be the way we will do it. So remember, again, next week is still my lecture class. All right, but I will ask my GAs to also attend, and I will start briefing you on the CAs in addition to talking about relative degree greater than 1. All right, but I'll start briefing you on the CAs. That will be next week, lecture 5. Then lecture 6, remember, you better start looking at Prof. Ho's materials. All right, because Prof. Ho needs to start early in lecture 6. Then recess week. Then week 7, that lecture, I come back for the last time for my part. All right, where I will show you the way ahead. I will also tell you exactly for my part, which part is for exam, which part is not for exam. All right, then week 8 onwards will be all by Prof. Ho, okay? And he will also soon start telling you the requirements for his own CA2, both for 5104 and 6104. Okay, with that, I'm done with the matters for tonight's class. Let me stop the recording.